In this part, we'll see how steam seals work. Specifically, we'll see how a Gland steam seal system and a Gland steam seal exhaust system keep steam from leaking out and air from leaking in at the points where the shaft passes through the turbine casing. To understand how these systems work, it's helpful to know how pressure varies in a turbine. The pressure inside a turbine varies with the load. At low loads, many of the later stages in a turbine may be under a vacuum. As load is increased, more and more of these stages start to operate under pressure. Finally, at full load, only the last few stages of the turbine may actually be under a vacuum. In the stages that are under pressure, steam tries to escape from the turbine. The most likely place for this to happen is where the shaft penetrates the turbine casing. If the steam were allowed to leak out, it would affect the efficiency of the turbine because it wastes the steam. Leaking steam could also seriously burn personnel working around the turbine. In the turbine stages in which pressure is less than atmospheric pressure, air will try to leak into the turbine. This reduces turbine efficiency because the air must be removed in order to maintain the vacuum. Air leaking in also can cause a thermal stress problem in the turbine. The outside air can be much cooler than the inside of the turbine. And when cool air gets into the turbine, drastic temperature changes occur. The resulting thermal stress on turbine parts could cause them to crack. One way to keep steam from leaking out of a turbine and air from leaking in is to use Gland steam seals. This Gland steam seal is made up of several labyrinth seals. A labyrinth is defined as a maze or tortuous path from which escape is difficult. The maze in a labyrinth seal is a set of grooves and ridges which correspond to another set of grooves and ridges on the turbine shaft. The labyrinth seal creates a tortuous path or maze. The maze restricts flow, making it difficult for air to leak in or steam to leak out between the turbine shaft and the casing. The inside of the turbine is in this direction, and the outside is in this direction. There are 3 seals being used. Generally speaking, 3 or more seals are used at each sealing point. The seals collectively make up a gland. The Gland steam seal system is connected to the gland at this opening, and the Gland steam seal exhaust system is connected at this opening. We can use this illustration to show how these systems work. The illustration shows 2 turbine sections, a high-pressure section and a low-pressure section, each connected to the same shaft. Here is the Gland steam seal system, and here is the Gland steam seal exhaust system. We'll look at the Gland steam seal system first. The system is made up of a steam supply line, a steam supply control valve, a steam leak-off line, and a steam leak-off control valve. When the turbine is operating at low loads and many stages are under a vacuum, outside air tries to leak in. In response to these conditions, the Gland steam supply control valve opens and low-pressure steam is supplied to the glands. Part of the low-pressure steam supplied to the glands enters here and flows toward the outside past the second seal. The remainder of the steam flows into the turbine. It's the flow of steam towards the outside of the gland that prevents outside air from leaking into the turbine. Steam flowing into the turbine from the glands presents no real problem, since the leaking steam simply mixes with steam that is already in the turbine. So when a vacuum exists inside the turbine, the Gland steam seal system supplies steam to prevent air from leaking in. When the turbine is operating at full load with a positive pressure in most of the turbine, air leaking in is not a problem, except near the last stages, which are still under a vacuum. Where the pressure is positive, steam must be prevented from leaking out. In this case, pressure in the gland is increased by steam leaking from the turbine. The steam supply valve closes because steam no longer needs to be supplied from outside the turbine. If the pressure increases to a certain point, the steam leak-off valve opens to prevent pressure from getting too high. Steam that passes through the leak-off valve is directed to a low-pressure area such as the main condenser. Now let's turn our attention to the Gland steam seal exhaust system. The purpose of the exhaust system is to draw off steam leaking past the second seal before it escapes to the atmosphere. The system also pulls out any air that's leaking into the turbine. A typical Gland steam seal exhaust system consists of a Gland steam condenser, one or more blowers, which are called gland steam exhausters, and connecting pipe. An exhauster draws a vacuum on the entire system, pulling air and steam from the glands into the gland steam condenser. In the condenser, steam is condensed, and the condensate is usually drained. Air and any other non-condensable gases are discharged to atmosphere by the exhausters. Normally, the gland steam seal system and the gland steam seal exhaust system work automatically. However, since both your safety and the efficient operation of the turbine unit depend on them, periodic checks are needed. The gland steam seal supply pressure should be checked to make sure that it is high enough to maintain the seals, but not so high that steam leaks from the glands. The temperature of the cooling water flowing through the gland steam condenser must also be checked. The temperature must be low enough to ensure that condensation is occurring properly. You should also make certain that the exhausters are working properly and that there's a vacuum in the condenser. And finally, check to make sure that the condensate water level in the gland steam condenser is being maintained at the proper point. There's usually an indicator that allows you to determine the condensate level. We've seen how the gland steam seal system and gland steam seal exhaust system work. We've also reviewed some common checks that are made on these systems. The points where the shaft passes through the turbine casing must be sealed to prevent steam from leaking out of the turbine and air from leaking in. Several types of seals are used to prevent these conditions from occurring. Probably the most common seals are steam seals, but two common alternatives are carbon seals and water seals. This is a cutaway view of a carbon seal. Carbon seals are usually found on low-pressure turbines because they can't withstand very high pressures. A carbon seal consists of one or more carbon rings held in place against the shaft by springs. As the shaft turns, it rubs against the carbon rings, and an effective seal between the shaft and the rings is achieved. Carbon, being softer than metal, creates minimal wear on the turbine shaft. Eventually, the carbon wears down, so the carbon rings must periodically be replaced. A second alternative to steam seals is water seals. When water seals are used, water is pumped through a special gland to minimize leakage. A gland is a device used to create a seal. The advantage of water seals over carbon seals is that their parts tend to last longer. A typical water seal uses an impeller that's mounted on the shaft to circulate water through the gland. The circulating water fills the opening between the shaft and the casing, preventing leakage. Valves in the water supply and return lines maintain the proper water pressure in the gland. This design allows some water to leak out of the seal. For this reason, shrouding is placed around the turbine shaft on each side of the seal. Water collects in the shrouding and is drained off by connecting drain pipes. As with all turbine systems, sealing systems should be regularly checked to make sure they're functioning properly.